Hello and welcome to lesson 5.4, limits involving infinity. So recall the end behavior of a familiar function, for example, a rational function. Now rational functions, please remember that they could change, that they have vertical and horizontal asymptotes in many cases, not all cases, but many of them. And as you can see right here, there's a vertical asymptote and a horizontal asymptote for this function. The function's equation has actually been given off to the side. Well, you can describe the end behavior here in different ways. So as x approaches infinity, the y value approaches 2 from below. So you can see that there. As x approaches negative infinity, you can see the y value approaches 2 from above, which you can show right there. And remember, this is the proper notation that you'd use for it. You don't necessarily have to put the below and above, but I find it helps. And as well, as x approaches the value of -1 from the left, you can see the y value gets closer and closer to positive infinity. And as x approaches -1 from the right, here on the graph, y approaches negative infinity. Well, as you'll notice, in all these instances, here we have limits, because you're getting closer and closer to the values, that actually are involving the value of infinity. While limits that involve the value of infinity only can approach from one side and cannot approach from both sides. So, as the value increases without bound, positively or negatively, we are looking at determining whether a horizontal asymptote occurs. And that is what we call our horizontal asymptote, and we're actually looking for the limit as x approaches infinity for your function f of x. See if it actually equals a value L. If it does, then you've got a horizontal asymptote on that side, on the right-hand side. Or you're also looking at the limit as x approaches negative infinity for that same function. See if it equals some limit. Let's call it L. So if it doesn't approach a value, then the limit does not exist, and therefore the end behavior might not be actually approaching a horizontal asymptote. So for example, let's change the color back to red here. With our last item, calculate the limit as x approaches infinity of our function 2x minus 3 all over x plus 1. Well, in the past, you saw that leading coefficients actually take control. So this 2x and the x take control, because as the x values get extremely large, the -3 and the 1 don't make much sense. So you take your 2x, you divide by x, and you get a value of 2. Likewise, if you take limit as x approaches negative infinity for the same function, again, that also approaches 2. So that means, therefore, you have a horizontal asymptote of y equals 2, that horizontal line. Okay, so moving right along. The limit properties for definite limits also work for indefinite limits. That means a definite limit, if you were curious, limit as x approaches some value a for the function f of x. That's what we call a definite limit. Whereas indefinite limits, limit as x approaches infinity for a function f of x, those properties still work out. So for example, if we were talking about calculating a limit as x approaches a for the function x, that equals a. Whereas if you're calculating the limit as x approaches infinity for the function x, that approaches infinity or equals infinity. Now, if we do approach a value infinity, we can actually list it as infinity, or we can also say it does not exist. So as a limit gets closer and closer to a value from either side, but approaches an infinitely large value, then we have a vertical asymptote. So, limit as x approaches some value, let's say a from the left for your function, equals plus or minus infinity, and or limit as x approaches a from the right for your function f of x, again, approaches plus or minus infinity. So that way you can see that you approach a vertical asymptote. So in our last example, let me change the color here. Let's say we were looking at the limit as x approaches the value of -1 from the left for our function that we had 2x minus 3 all over x plus 1. So what you do is you choose values that are very, very close to -1, but a little left of -1. So that means the denominator is going to be a negative. Also, the numerator is going to be a negative. So both values are going to be positive. However, the value on the top is going to be larger, much larger, than the value on the bottom. So if the value on the top is larger than the bottom, and the bottom is getting closer and closer to 0, this is actually approaching positive infinity. You can try practicing values if you like to see that. Likewise, limit as x approaches -1 from the right for the same function. So again, you choose values of -1, very close to -1, but on the right, so positive values, or closer to the positive values. Again, the value in the denominator is going to be a really, really small value. The value in the numerator is going to be a really large number and negative. So this is actually going to give you a negative infinity. Oh, and the denominator is a positive value. So let's try this again. Let's determine the limit as x approaches 3 from the right for the function x over 3 minus x. So how you might want to do it, or how you might want to think about it, sometimes I put it in 3 plus over 3 minus 3 plus. Well, what you'll notice is your denominator actually turns out to be a negative small number. The numerator, and this I'm just writing off to the side here, the numerator turns out to be a plus big value. Well, in that case, that's going to give you a minus bigger value. So that limit that we're actually calculating right here actually tends towards negative infinity. And you can prove it to yourself by drawing a little sketch of the function, if you know what the sketch is, or you can use your graphing calculator to do this. And you can see the function goes like this. This is the value at x equals to 3. And your function looks something like this. Oh, sorry, not so high there. Should go a little lower, as it does have a vertical, horizontal asymptote. And there we go. Okay, so let's move along. An end behavior model is actually when you can find a function g, so that when you find the limit as x approaches plus or minus infinity for the function f of x divided by g of x, you get a value of 1. So the function g is called its end behavior model for the function f. So let me show you what I mean in another example. Okay? So right here, you have this limit as x approaches infinity of 2x cubed minus 4x squared plus 5x minus 3 all over x cubed. Well, what I could do is I can actually divide this function right here. I can divide the numerator by x cubed, and I can also divide the denominator by x cubed. So what happens if I do that? So that numerator turns out to be 2 minus 4 over x plus 5 over x squared minus 3 over x cubed. And my denominator just turns out to be 1. Well, from there, what I could do is just make my life a little bit easier and actually separate these into multiple limits. So limit as x approaches infinity of 2 minus limit as x approaches infinity of 4 over x plus limit as x approaches infinity of 5 over x squared minus limit as x approaches infinity of 3 over x cubed. Well, if you notice anything about these functions right here, you'll actually notice that the 4 over x, the 5 over x squared, and the 3 over x cubed, as you get infinitely large values, the denominator takes over, getting very, very large. The top number is very, very small comparatively, and each one of these actually tend toward 0. So this is a common way we write that it tends towards 0. So this one also tends towards 0, and this one also tends towards 0. Excuse me. So based on our limit properties, I know this is going to be the value 2, this one's going to be 0, this one's 0, and this one's 0. So this overall limit turns out to be 2, which is the end behavior of this function. This actually tells you what the function is going to get close to as time progresses. And therefore, an end behavior model of this is x cubed over x cubed, or 1. So, therefore, 1 equals 2 is the horizontal asymptote. So actually, you didn't actually need to investigate the end behavior being 1. End behavior model being 1. Okay, so let's take a look at some other possibilities. So here we're going to determine the end behavior models for these two functions. So for my numerator, I'm going to divide by, well, my numerator is an x to the 4. So I'm going to divide by, in the numerator, x to the 4. And in my denominator, I'm going to just divide by a 2x squared, because that'll get rid of the leading coefficients. So that's going to give me the limit as x approaches plus or minus infinity for this function f of x is actually going to turn out to be limit as x approaches plus or minus infinity of 1 plus 3 over x minus 1 over x cubed plus 1 over x to the 4 all over 1 plus 5 over 2x minus 2 over x squared. Well, all parts of these go towards 0. This is going to give me a value of 1, which is exactly what we want for our end behavior model. So therefore, let me change this back to red. Therefore, our end behavior model is x to the 4 over 2x squared, which is x squared over 2. So if you actually graph this, you're going to see that the end behavior of this function looks like it is following the function y equals x squared over 2. So let's try that again with that part B. So we're going to divide the numerator by 5x, and we're going to divide the denominator by x squared. So the limit as x approaches plus or minus infinity for this one, for the function g of x, divided by that 5x over x squared. Sorry, I should have done that up here as well. Oh no, actually I already wrote it there. Equals, let's see, this will be 1 minus 3 over 5x. Oops, limit. I forgot the limit there. Let me fix that. Limit as x approaches plus or minus infinity of 1 minus 3 over 5x all over 1 minus 3 over x plus 7 over x squared. So again, all of them tend to 0 except for the 2 1s, which give you a value of 1. So here, our end behavior model. Which is just 5 over x. Now if you notice, the limit as x approaches plus or minus infinity of 5 over x is actually 0. So this actually tends towards the function 0 as time goes on from both positive and negative values. Okay, so last thing I should mention, note that not all end behaviors are the same on both sides of a function. So for example, f of x is equal to x plus 2 to the exponent negative x. You can use g of x for the right hand side, and you can use h of x for the left hand side. And then you'll see the end behaviors on either side tend towards 1 on either side. Now if you're able to graph this and look at it, I'm not able to include that, but you would actually see how it works out. So let's try it. Let's say the limit as x approaches infinity for f of x over g of x turns out to be the limit as x approaches infinity of x plus 2 to the negative x all over x. That reduces to 1 plus 2 to the negative x over x. I'm going to put brackets around that so I know that the limit applies to both of it. So I'm going to rearrange this. So limit as x approaches infinity, just for my own brain how it works. I'm going to put the 2 to the exponent x times the x in the denominator. So as x gets really, really large, you're going to see that this value right here tends towards 0. So this limit turns out to be equal 1, which is exactly what we want to see. But, however, let's take a look at it from the right-hand side, approaching the left-hand side, sorry. So as we approach negative infinity, we're taking f of x over h of x. Okay, so here we're going to get x over 2 to the negative x plus 1. Again, for my own sake or my own brain, how it works, I'm I'm going to rewrite this as x times 2 to the exponent of x plus 1. Well, as x gets infinitely large but negative, please realize that we do actually have two values here. This value and this 2 to the x. Well, we do know that 2 to the x grows a lot faster than x. So if that's the case, this value is going to actually tend towards 0 quicker than this one. And therefore, this piece is going to be dominant. And that's going to tend towards 0. And therefore, our limit turns out to be a total of 1, giving you this end behavior. So again, I encourage you guys to actually sketch the function f of x and compare it to g of x and h of x and see how the ends of the functions look the same. And thus concludes this lesson.